Hi, we're the Clueless, team number 11212 from San Diego, California. This is our YouTube robot explanation video, where we'll be talking about each subsystem of our Centerstage robot, Rush. So we're a 14-person team, and the way we divide our team is into three main sections. Those three are mechanical, software, and then our outreach team. Within each of these three sub-teams, we do have smaller sub-teams and leads. For example, our mechanical team is further divided into CAD, fabrication, and assembly. Our software team is further divided into autonomous and teleop. And then our outreach team is further divided into connect, business, and then impact. So talking about the number of members we have per sub-team, we have about 9 members in mechanical. We have 3 main members in software, and then 2 members in our outreach. But multiple members also do multiple sub-teams as well. At the beginning of this season, our main goal was to qualify for the World Championships. And to do that, we had 3 main goals in terms of our robot performance. We wanted our robot to be highly efficient, highly robust, and highly reliable. So at the beginning of the season, we spent about the first 3 weeks planning out our robot design, coming up with different concepts. During this time, what we like to do is we often use Tinkercad to make just brief robot CAD models, and then we shift over slowly to Fusion 360 or SolidWorks, where we make more finalized models that we display to the team during our full team meetings. And oftentimes this involves trading different ideas and trying to figure out what the pros and cons are of each idea. So actually at the beginning of the season, we had a very more complex design of our end effector system, but by trading out different ideas and combining multiple ideas together, we came down to this design, which we have now, and we'll be talking about it. After those first 3 weeks of brainstorming and prototyping, then we shift over to our CAD phase, where we spend a lot of time CADing each subsystem of the robot. And this involves a lot of testing and a lot of iterating. So we like to divide our week into some days, like the beginning of the week, dedicated just to fabrication, where we make all of the parts in-house or 3D print any parts. And then later in the week, around Friday, Saturday, and Sunday, we have 5-hour build meetings each, where our mechanical assembly team comes in and they assemble the subsystems together. And then throughout the whole entire week, CAD is working until we get to a solid first robot version. After that, then we go into the optimization phase. So we optimize primarily by watching past robot clips. So we'll take minutes or hours of teleop footage and just analyze that and see how we can improve. We also like to take inspiration from our past competitions, because usually our first few competitions we don't perform well. So we learn from those mistakes and we try and improve them. And this often involves a lot of analysis of auto and teleop. And then we go back to the drawing board and figure out how we can make the design more efficient or more reliable. So that's the majority of the season is optimization. And then towards the end of the season, or like before we have large competitions, then we'll start to work on our competition material, such as our engineering notebook, our portfolio, and we do a lot of presentation and Q&A practice.
Our drivetrain is a standard parallel plate mechanism drivetrain. Our power transmission works from these 435 RPM motors that power these 24-teeth go build-up pulleys, and those power a 16-tooth 3D printed pulley that's directly attached to the mechanism wheel. And then our mechanism wheels rotate on dead axles, meaning the axle itself is screwed in place, and the wheel and the pulley system rotates around the axle. In addition, the 2 pods are connected basically from this 12-rex aluminum go build a shaft, as well as this 3D printed frontal part and the intake. So we considered having a U-channel or a low-side U-channel here, which are more common. However, we realized that since we would already have so many subsystems that are connecting the 2 sides, we wouldn't need the extra strength that it would provide, and we didn't want to have it take the extra space. Lastly, all of our motors are located close to the ground because we wanted to keep the center of mass low so that when we extended our slides, the robot wouldn't risk tipping. As for materials, we started out having all the entire drivetrain made out of Delrin. However, we realized that Delrin was flimsy later on, so we opted to switch to aluminum side plates for the outer plates while keeping Delrin on the inside to save time. And then for the aluminum side plates, we also cut out these holes where the pulleys are. And this just gives the pulleys a little bit more clearance so that when they're rotating, they're not going to rub against the outer side plate.
This is a odometry system of our robot. So for our odometry, we're using a 3-wheel odometry system. So we have 2 vertical odometry and 1 horizontal odometry pod. So for these odometry pods, these are all custom made. So these are all 3D printed because the reason why we made our own odometry is because we realized that there's no odometry that's open source and that is as compact as we want it. So we realized that there's no odometry system that can fit in between here. So we wanted to design our own. So this is we think this is a more compact than any odometry that's currently available. So the way that we did this is by it's very similar to Looney Odo, where you take apart the rev encoder, rev throughbore encoder, and then you print a case on the other side. So we did it such that the odometry is kind of offset from the axle, so that you can actually push it in even further. So the entire thing is even more compact than the Looney Odo. Yeah, and in terms of the width, again, everything is super low profile, just to make sure it fits between the belts without rubbing. Yeah, and then for the springing, we have a lever arm on the top, and then we have a spring attached to it. So before we were using rubber bands, but we realized that rubber bands, the tension gets worse and worse over time. So we switched to springs for these, and springs are a lot more reliable and they're a lot more consistent over time. And so we spring these with about 2 to 3 pounds of force on every one of these. It's just to keep it consistent so that the wheels don't slip. And we found that over entire match, we have around 0.7 inches, plus minus 0.7 inches of air. So it's pretty good. This is our intake. Our intake has 3 stages. So the first stage is a drop down actuated by this servo. And then the 2 other stages are at the back, they're stationary. So basically the first stage will allow us to get pixels off of the stack. For all 3 stages are using custom 3D printed TPU spokes. So for the first stage, they're really soft and small. This is to help get the pixel off the stack easier and more controlled. On the second stage, the rollers are a lot bigger and they're a lot stiffer. That allows us to quickly intake the pixel and shoot it into the third stage. On the third stage, instead of using spokes, we use wheels with some small spokes on them. This will allow us to be a lot more controlled for the pixel when it enters the transfer area. This ensures that it's at the same speed. So before we use this design, we initially started with a uptake like this for all 3 of these, but we realized that it wasn't very consistent because sometimes the pixel will shoot out really quickly, but sometimes it'll be really slow. So we decided to switch to these wheels. But we decided to keep one of the optics because we found that the reliability of transfer were a lot higher with the optic here. Moving on to the powering system for intake. So on the back, we have this motor right here that drives 4 gears to power the bottom roller. And the motor also has a pulley on it that goes up and drives the top rollers.
For our lift, we have 4 stages of Star 230 linear slides, and we have two sets of them, one on each side, which allows it to be very stable. This won't really shake. And we also support that with these 3D printed cross beams here. And all of that together means that the slides, when they're up, it's not going to give us a lot of shaking issues. It's very sturdy. In addition to that, the way that we connect all of these together, we have these slide inserts. And so these are vertically strung, which means the bearings that have the string on them are mounted vertically. The reason why we chose to do this is because it makes the width between each slide a lot more compact, and so we can fit a lot more in between the final stages of the slide. So you can see the string routes continuously along each bearing, and then we spool it around this central spool here. You'll notice that all of our spools, so the extension, retraction, extension, are on the same axle. The reason why we do this is so that it's mechanically linked, which is beneficial, so that if you spin one motor more than you spin the other one, it's not going to cause the slides to go sideways. It'll always be perfectly vertical up and down. Okay. The way we power our slides, we use 2 motors down here, which are 435 RPM motors, and those are belted on the left and the right here. That all belts to our axle that we run the spools on. So that way it's mechanically linked, and we're able to package the motors very nicely in front of the slides. So obviously the space right here, because we have the angled sides, we knew that we probably weren't going to use that space for anything else, so it just made sense for us to use this kind of packaging there. In addition to stringing our lift on the bottom of the slides, you'll see that we also have counter springing on the top through these bungee cords. So essentially how this works, when our slides are all the way down, the bungee cord is tensioned at the maximum because the distance across all the slides is at its most. And so as we raise the slides up, that distance decreases because obviously the distance between your bearings decreases. And so the tension that the bungee cord has decreases as the lift raises itself. This means that we're able to counteract the force of gravity at any position with the slides. And even without the motors holding the slides up, we're able to hold our position, which allows us to be a lot more precise with our deposits. The way we string this is basically the way we string normal slides continuously, except instead of spooling it around an axle, instead we spool it around this counterspringing module right here. So you'll see the bungee, it ties off at the top, it runs continuously all the way down to this bottom insert, and then it just goes into this 3D printed module. This module has a bunch of V-groove bearings inside it, and we just loop the bungee around it as much as we can. And that allows us to increase the length of the bungee cord and make it more linear. So you'll notice as we raise the slides that it's pulling the excess bungee in here. As we lower it down, it's also running it across those bearings. And so that allows the counterspringing to be a lot more linear while being very compact.
So this is our claw system. So our claw deposit system basically is able to grab 2 pixels vertically at the same time and then deposit them one by one. This is probably one of our most unique parts of our robot. So our entire mechanism is driven by just one servo to grab both of these pixels. The reason why we chose to only use one servo is because we want to minimize the weight. Because the lighter the weight, the faster you're able to swing the arm over, and the faster the cycle time will be. We chose to use a Pro Modeler servo right here. The reason why we chose a Pro Modeler over an Axon is because it has a higher output, so it has a higher torque and also higher speed. The downside of this is that it is a little bit more expensive than the Axon, so we only have 2 of these in our garage. And for our claw, for the claw, both of these are springed by the rubber band. So basically the bottom claw is directly driven by the servo, and the top one is offsetted in a little bit, and it's driven by this rubber band right here. So basically you can push it out. So when you grab the second pixel, it'll be level, and then when you drop it, you can open the bottom claw, and the top one will still stay in because of the rubber band. And there's an end stop right here to just prevent the claw from going in too far. And the reason why you have an end stop is just so that the claw doesn't go all the way in, so you can still transfer the pixel properly. And also for to help with the transfer, on the top you have this kind of top plate. This top plate just helps to guide the pixel in. So as you can see, when it goes down like this, it matches perfectly with our intake, so that the pixel has nowhere to go other than to go into the claw. So this has near perfect transfer accuracy, reliability. And also, in addition to this top plate, we also have this kind of finger thing built into the top plate. So this is just to help us to reorient the pixels on the board. So basically, you can flip this claw over like this, and then use this finger to move the pixels around on the board. And actually, in the world record match that we did, 416 points, when we partnered with Roboctopi, we actually had to use one of these to move the pixel over to make the 5th mosaic. And also, it was also the first time a team has ever done a 5 mosaic in a single game.
So this end effector design is actually not the idea we had initially in mind. Our original idea was very similar to Wolfpack's power play end effector, in the sense that there were counter rotating turrets, and then there was also a V4 bar system. So essentially the idea was that we would be able to deposit anywhere on the board without having to move the drivetrain as much. And we did implement this for our first 2 San Diego competitions. And what we found is that this design was overly complicated, in the sense that it was difficult for both drivers to control and for software to autonomously control. So we simplified to an end effector design, which had one pivot right here, another pivot right here, and then our claw itself was on the end. And this ultimately proved to be a lot more effective. And in my opinion, I think it helped us win the World Championships because we're able to optimize this system so much. Also, in terms of our claw, we initially didn't have the idea of the claw. We had an idea of a bucket deposit. So essentially it was a type of bucket that would hold 2 pixels and then individually drop each of them, or be able to drop both of them at the same time. But as well, that system did not prove to be as simple as possible, and it definitely was not reliable. So we simplified the design down to this claw, and it proved to be a lot more effective. In this section, we'll be talking about our hanging system on our robot. So our hanging system has gone through many iterations. If you saw our earlier competitions, you saw that we had a tape measure that was directly attached to a motor. And after many different iterations, we realized that was inefficient and it's not always reliable, because sometimes our hook would break off of our tape measure. And then we pivoted to a system where we had magnetic hooks on these arms that were actuated by axon servos. That system was inefficient in the sense that the hook detaching off a magnet wasn't too reliable. So we decided to come up with this system where the hook is directly attached to the arm. And this system is powered with 2 axon maxes. It's mirrored across this axis of our robot. There's 1 axon max here and 1 axon max here. The axon max is in its own custom servo block with a bearing that encloses the servo horn. And then on the end of the servo horn, we have a spool with Kevlar lined string. So this spool is able to rotate, and you'll notice that the hook is moving in this direction. And that's because we have this tension right here. So this is elastic bungee that we purchased off Amazon. And essentially this wants to pull this whole arm with the hook in this direction. So the thing that's holding it back is the string that is attached to the servo. So you'll see as I unspool this, then this arm with the hook will move backwards. And then once we're under the truss, then we'll be able to lift ourselves. In terms of materials, this is all CNC'd in-house. This is 1/8 inch aluminum with a 3D printed ABS spacer right here and another CNC'd hook. And we had to optimize the shape of this hook just to ensure that there wasn't too much overlay in the hook, such that it was harder for the drivers to control and get onto the truss. So that went through multiple iterations as well. In terms of the mounting for the pivot system in the back, we have another CNC'd 1/8 inch aluminum bracket right here. This mounts directly to our Delrin plate, which is also supporting our hubs. And then there's an ABS bracket right here with standoffs that are used in order to support this part of the arm, which has a bearing inside. So this can pivot freely like that.
Okay, so this is our drone launcher. So basically how it works is we have this MGM rail here, and the entire mechanism rests on this carriage. So basically it's spring sprung with these bungees on both sides. And these bungees are wrapped around with bearings, and this is to ensure that the length of the bungee is longer, and this will ensure a more consistent launch acceleration. So when it's preloaded, the servo will come back and latch it, and when you want to release it, you will just rotate the servo arm down, and it'll shoot the entire thing forward. On the carriage, the plane is held upside down, so there's a little slot right here for the tail of the airplane to go, and there's also space over here for the wing of the airplane. We found that having the airplane sit upside down is much more reliable than having it upright, and the reason for that is when you launch it, the angle of attack on the wing would be 0 degrees, rather than having it rest on the fuselage, which would make the angle of attack negative, and it wouldn't be consistent. And also another thing we did on the airplanes is that for the airplane, on one side of the aileron, we tilt it upwards, and one side of the aileron, we tilt it downwards. And this will make the plane roll, and this will make the launch a lot more consistent.
So for our sensors, starting off, we have a Logitech C920 rear-facing camera, and we use this for detecting the backdrop during autonomous period. In addition to that, we have a rear-facing ultrasonic sensor. This is a URM09, and we use this to detect our partner robot during autonomous to make sure we don't collide with them during that period. You can see in the transfer here, we have a Rev V3 color sensor, and we use that to detect the 2 pixels when they've been intaked. So one will go in there and we'll see that 1 pixel, and then when we see the 2nd pixel, we'll know that we've intaked 2 pixels. And then our deposit picks that up and flips around. And then we have this limit switch here, so that when this hits the backdrop, we know that we're in the right position to drop our pixels.
So we're going to talk about the wiring for the robot. So in terms of the wiring on our robot, we have a lot of custom wires. So we actually make just a wire, and then we'll crimp both ends and add connector to them ourselves. The reason why for that is we want to have the most amount of control over the quality of our wires. So for example, for the length of the wire, we want to make sure it's custom. So it's just a perfect length between the 2 parts that we're trying to connect. So there's as little excess wire as possible. So starting with the hub mounting, the 2 hubs are mounted here and here. This is the control hub, and that's the expansion hub. So having the hubs mounted vertically, that would just make sure it's very compact and out of the way of the subsystems. In the beginning, we considered mounting the hubs over the intake like flat like this, but we realized that we need to mount the battery somewhere, and mounting the battery on the side will make the robot balanced uneven, and also we wouldn't have space to mount the hanging system. So that's why we decided to put the hubs on the side and have the battery in the middle. And for the wires in between this, we have a crossbeam, and that's also what the battery mounts to. So the wires we actually route it along the crossbeam between the control and expansion hub, and the battery wire also connects to these wires and goes to the control hub. And going down over here, this is our SPM, servo powering module. So SPM increases the voltage for the servos and makes them run faster with higher torque. So basically, right now we only have 2 servos plugged in. So we only have 2 servos for the hanging system because on the SPM we realize that there's some reliability issues. So in the competition, when we run the servos too fast, so it sometimes actually burn the port out. So we decided to put only the hanging servos onto the SPM because we're using servos to lift the robot, and they need to be pretty high torque. So before we actually had the deposit system, these 2 servos in the SPM, but sometimes the SPM is just not as reliable as we want, and so that's why we just keep the servos without the SPM. And so the wires coming out of the control and expansion hub, they will go through the snakeskin. So this snakeskin is another thing that connects between the control and expansion hub, and these are the wires that goes for the servos that goes from the expansion hub to the top. So we're using a snakeskin to cover all the wires. The reason why we use a snakeskin is because we want to make sure that all the wires are like together and they don't just like flop around. So it just makes the wiring a little bit cleaner. And so the wiring is everything is zip tied to the size inserts. So when you collapse it, the wire kind of goes together nicely. Yep. And going up here, we have some servo clips, and the reason why I use servo clips is because servo clips make sure the connector doesn't come apart. So just make sure the robot is as reliable as possible. And going up here for the arm, actually we designed it so that we can route the wires through it. So the inside of the arm is hollow, and you can put the wires through. But the reason why we currently have some wires on the outside is because right before World Championships, we had some servos that we need to swap out, and we didn't want to spend too much time reworking the wires and taking the connector out and routing it through. So that's why we currently have some wires on the outside. But you could route everything through the middle, and that would be a little bit cleaner. So you can see like these wires are routed through the middle and just looks super clean. Okay, and another thing that we do to keep the wires clean and accessible is that in the front we have these access panels that we can actually open. So it's just one screw and the entire thing comes apart like this. So it just kind of opens and you can access these ports and do some maintenance inside the robot a little bit easier. So the reason why we have this is just to kind of protect everything, because we didn't want to get the wire sliced during a game. Again, it's just making sure everything is as reliable as possible, and also with this coverage, it just looks good. Yeah, and we just kind of 3D printed these hinges. It's very simple, and this is just a latch that you can screw onto. Yeah.